All right, so we're talking about electron configurations and Hund's rule and how electrons have to be added to degenerate orbitals to each one first, and then you have to pair up your electrons after each orbital, degenerate orbital, is halfway filled. And then you fill them completely after that. So this picture sort of shows you that trend. So the electrons occupying the orbitals in the outermost shell are called valence electrons. Okay, valence electrons have the highest value for the n, or the quantum number. The electrons occupying the inner shell orbitals are called core electrons. So the core electrons represent noble gas electron configurations. Electron configurations can be expressed in an abbreviated format by writing the noble gas that matches the core electron configuration along with the valence electrons. So this is a way to very quickly, it's sort of a shortcut into writing electron configurations, because basically instead of starting with hydrogen, we can start with the nearest noble gas, the noble gas preceding the element. So here, for example, we have the electron configuration for sodium. It's 1s2, 2s2, 2p6, 3s1. Its valence electron is represented by 3s1. Here are the core electrons there. So we can substitute those core electrons by using the nearest noble gas. So for sodium, let me go look here. So for sodium, the nearest noble gas preceding the element is neon. So the electron configuration for neon is 1s2, 2s2, 2p6. So we can start with neon by basically showing, where am I at here? Showing the abbreviation for neon. Okay, so the abbreviated version of the electron configuration would be writing neon in brackets and then writing your valence electron 3s1. So abbreviated electron configurations, here we have some examples. For lithium, you're starting out with helium, okay, and so its electron configuration would be written as helium in brackets and then 2s1. I'm sorry, I'm trying to find my place here. Okay, so for sodium, we already did that one, 3s1. For potassium, we're starting with argon. Okay, with potassium, we're starting out with argon, and then it's going to be 4s1, would be its abbreviated form. If you notice, though, notice the all of group 1 metals here have pretty much similar electron configurations in that they all have one electron in an s subshell. And then group 2 elements here, using the abbreviated form, beryllium, you're starting with helium, it would be 2s2. With magnesium, here, you would start with neon, and then it would be 3s2. Okay. Calcium would be start with argon, and it's 4s2. Again, notice this similarities here. 2 electrons in an s subshell for group 2. So when you're talking about electron configurations for transition metals, you're having to basically add electrons to it through the 3D subshell. So D subshells are filled to capacity with 10 electrons, right? We know that if we count from left to right here, there are 10 electrons here, 10 elements here, 10 elements here, which represent 10 electrons, 10 elements here, etc. So after the 3D subshell is filled, electrons are added to the 4p subshell. All right, so electron configurations for the 2 periods of inner transition metals, lanthanum through lutetium, actinium through lawrencium, electrons are added to the F subshell. So let me show you where that's at. So if I zoom in here, you can see, you follow the atomic numbers. So you see it's atomic number 56, or 55, 56, 57, and then 57 goes to 58. See how that goes there? So when you're going through here, okay, you have to go through the F block, okay, 71, and then you go back up here, 72 on. You're following the atomic number, right? 86, radon, 87, 88, 89, actinium, and then you go to 90, okay, all the way to 103, and then you go back up to 104. Okay, so you're following the atomic number as you're going along here. All right, so that's what they're trying to tell you, to make sure when you're writing the electron configurations for elements that are in the F block, make sure you know how you're going to get there. Okay, when you have to go down to the F block and then go back up. All right, so over here, so electrons are added to the F subshell. Okay. There are some exceptions to the order of filling subshells. So here it's generally with D subshells you have a problem. So some exceptions here, copper and chromium. So there's a stability associated with a half-filled or fully filled D subshell. So a half-filled D subshell would have 5 electrons. A fully filled D subshell would have 10. An electron shifts from a 4s into the 3d subshell to achieve this stability. So for example, what would we expect the abbreviated form for copper to be for the electron configuration? So let's figure that out. So for copper is right here. Okay, so our nearest noble gas preceding it would be argon. So it would be argon in brackets. And then we would expect its electron configuration to be 4s2. And then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d, 9. All right, so that's the expectation. Okay. 4s2, 3d, 9, starting out with argon. Actual is 4s1, 3d, 10. So why is that? Well, copper is going to prefer a full D shell over a full S shell, all right, or subshell. So what that means is that we need to, when we, since we only have 9 electrons left, we're going to completely fill the D subshell and then just take 1 from the S. With chromium, if we look where chromium is, it is 4 electrons into the D subshell. And again, with chromium, it wants to have at least half, or all of it, right? It wants to have at least 5 electrons in the D subshell, or 10. So it only has 4. It's so close. So what is it going to do? It's going to pull an electron from a 4s subshell. So again, when we're talking about exceptions here, this would be the expected electron configuration for chromium, 4s2, 3d4. Because it wants 5, a half-filled D subshell, it's going to pull 1 electron from the S subshell. So when you get to a point where you're doing electron configurations, when they're these guys here, or these guys here, you're going to have to take 1 out of the S subshell. All right. So here we're going to switch over to an example where we're trying to determine the electron configuration and the orbital diagram and the quantum numbers for phosphorus. All right, so here we have example 6.10 from your textbook. They're wanting to know the electron configuration, orbital diagram, and the quantum numbers for the last electron for the element phosphorus. So let's go ahead and figure out our electron configuration for phosphorus. I'm going to refer to the periodic table. So here we have phosphorus right here. It has 15 electrons. So its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p3. Okay. So I have that written there. 1s2, 2s2, 2p6, 3s2, 3p3. All right, so the orbital diagram, I always write that out by first writing out the electron configuration. So I write the N value and the subshell value, whatever letter that happens to be, 1s here. S subshells have one orbital, so I draw one box, right? The 2s, again it's an S, so one box. 2p, so p subshells that have 3 orbitals total, so 3 boxes. Okay, so if you wanted to make a list here, if you have the subshell and then the orbitals, I think I already made this list before. If it's S, there's 1. If it's P, there's 3. D is 5, and it's 7 if it's an F. And now I'm squeezing everything in here. All right. So, and again, you can look at your periodic table and figure that out by looking at the number of elements there. All right. So notice I have draw out my boxes, and then there are 2 electrons there, so arrow up, arrow down. 2 there, arrow up, arrow down. 6 arrows, arrow up, 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 and then down, down, down. You get in the habit when you have degenerate orbitals, it's more than one orbital at the same energy value or N value. They're equal in energy, so you fill them up halfway first and then come back and pair them up, okay, after you fill them up halfway. 3s1, so arrow up, arrow down, and then 3p3, so arrow up, up, up. Okay, if you wrote arrow up, arrow down, arrow up, that would be incorrect. You should fill up, remember with Hund's rule, you fill up the orbitals halfway first, and so you should have 3 arrows pointing up. If you have 3 arrows pointing down, that's fine too. All right, so the last thing they wanted us to do was figure out the quantum numbers for the last electron. So what is the last electron? So the last electron I added was 3p1, or well, it's technically 3p3. 3 tells me the quantum number, p tells me the L value, and this 3 is not terribly helpful. It just tells me how many electrons there are in the 3p orbitals. So that's not very helpful. But these two, the number and the letter, these 2 pieces here, help me out tremendously. Because this tells me the N value. So N is 3, P is 1. Just remember our L values here, an L of 0 is S, an L of 1 is P, an L of 2 is D, and L of 3 is F. So if it's a P, I know it's a P subshell, so no, I know L has to be 1 in that case. Okay, and then the M sub L is just negative L to 0 to positive L. So negative L, or negative 1, to 0 to positive L, or positive 1. Okay. This tells me the orientation of the orbitals. So I went back and drew that in here. Okay. Here, this orbital could be negative 1, this is 0, and this is positive 1. Okay. Those are my orientations, okay, of my orbitals. That's what my M sub L number tells me. Okay, these numbers tell me that I have 3 different orbitals. I have 3 different numbers. They're at 3 different orientations. All right, so the M sub S value can be either plus or minus 1/2. Okay, so here, because my arrows are pointed up here, if this is my last electron, it's positive 1/2 would be the n sub s value. But if you drew your arrow pointing down, it could be negative 1/2, and that would be fine too. All right, so here is a set of numbers I could assign for my last electron. All right, so here are some of the numbers that have to be the same as what you got. So n has to be 3 because that's the quantum number. L has to be 1 because it's the last electron was put in a p orbital. M sub L can be one of 3 different numbers. It could be positive 1, it could be 0, or it could be negative 1. Depending on what you're calling which one of these is the last electron, you can say, well, it's this one, or it's this one, or it's this one. Okay? Or you could have numbered yours differently, starting with positive 1, 0, and negative 1. That's fine too. So there's some variation here. And then n sub s could be positive 1/2 or negative 1/2, again, because you could be writing your arrows down instead of up, and that's fine too. So if we really wanted to write out all the possibilities for the answer, it could be 3, 1, 1, positive 1/2, or 3, 1, 0, negative 1/2, or 3, 1, negative 1, positive 1/2. All right, so you see all the possibilities here. So 3, 1, negative 1, negative 1/2, 3, 1, negative 1, positive 1/2, 3, 1, 1, positive 1/2, 3, 1, 1, negative 1/2, 3, 1, 0, positive 1/2, 3, 1, 0, negative 1/2. So those are all the possibilities that you could have as answers, and they would all be correct, okay? Because, you know, you have variation in m sub L, depending on what you're saying is the last electron. And then you have some variation as whether you call it positive 1/2 or negative 1/2. So there's some wiggle room here, okay, in your answer. All right, so let's see, that's example 6.10. So let's move on into coming back here. All right, so the periodic table arranges atoms so that elements with the same chemical and physical properties are in the same group. Elements in the same group have similar valence electron configurations. So let me go back here, and they were trying to show us that trend. When they were looking at, you see how the valence electrons here are in the same subshell, and they have the same number of electrons in that same subshell? Notice that. All right, valence electrons play an important role in chemical reactions. This describes why elements in the same group have same chemical reactivities, because their electron configurations are the same in terms of, get back there, okay, in terms of there being one electron in the same type of subshell. The energy value is different, but the number of electrons in that same subshell is the same. See, group 1 has 1, group 2 has 2, and so on. So their electron configurations are similar in that respect. Okay. So main group elements are referred to as representative elements, are those in which the last electron added enters an s or a p orbital in the outermost shell. The valence electrons in the main group elements are those with the highest n level. Okay. Example, gallium. Okay, gallium has 3 valence electrons, okay, 4s2 and 4p1. The completely filled 3d orbital counts as core electrons, and they're not valence electrons. Transition elements are metallic elements in which the last electron added enters a d orbital. The valence electrons in these elements include d electrons. So an example here, we have vanadium, and it has 5 valence electrons, 3 in the d subshell and 2 in the s subshell. Inner transition elements are metallic elements in which the last electron added occupies an f orbital. So the valence electrons in these elements include F and D subshells. For example, promethium here has 7 valence electrons, 2 in the S and 5 in the F subshells. Okay, some of them also have D valence electrons in D subshells. Recall ions are formed when atoms gain or lose electrons. The cation is formed when one or more electrons are removed from an atom. So, for example, electrons that are added last are the first electrons removed. So that means that your valence electrons are going to be the electrons that are being removed to form a cation. For transition metals and intertransition metals, the highest electrons are lost first, and then the D and the F electrons are removed. Okay, so that's going to be a little bit different when we talk about those electrons from, if they have D and F transition valence electrons, then they're going to be removed from usually from an S first before D, and they're removed from D and F. Anions are negatively charged ions formed when one or more electrons are added to a parent atom. Electrons are added in an order predicted by the Aufbau principle. Okay. So here we're going to look at some electron configurations for ions. Okay. So the first step whenever we're trying to figure out the electron configuration for an ion is to write out the electron configuration for the parent atom and then add or remove electrons as appropriate. Okay. So here, for example, I have sodium. Okay. So for sodium, I'm going to first write its electron configuration for sodium, neutral sodium, and then because it's a sodium cation, a positively charged ion, I'm going to remove one of those electrons. Okay, so when I do that, here, the electron configuration for sodium, and here if we want to go back and look at it, for sodium it's going to be 1s2, 2s2, 2p6, 3s1. So that's the ground state electron configuration for sodium. All right, so because it loses an electron, you're going to omit this last term here, 3s1. It lost one electron, so it's going to lose it from the S subshell. And its electron configuration would be 1s2, 2s2, 2p6. Now, if you go back and look at your periodic table, that is the same electron configuration as neon. Okay, and what you're going to find is the reasoning why sodium loses one electron. It loses that one valence electron it has to have the same noble electron configuration as a noble gas, which is neon. All right, so magnesium, how many electrons do you think it's going to lose? Well, it's going to lose 2, so it can have, again, the same electron configuration as neon. All right, so there's a rationale why group 1 metals form +1 ions, or group 2 metals form +2 ions. Okay, and that's the reasoning behind it. And then when you look at its electron configuration, it makes it kind of obvious that this is the same thing as neon. Its electron configuration is exactly the same. All right, let's look at the electron configuration for phosphorus. I think we already did this one earlier. 1s2, 2s2, 2p6, 3s2, 3p3. So it's going to lose 3 electrons, okay? And so basically it's going to lose it from the p subshell. And so you're going to, instead of it being, it's going to be the same thing for the ion, except instead of it being 3p3, it's going to be 3p6 because it gained 3 electrons. Okay. So in this case, it's phosphorus -3, so it gains 3 electrons. So instead of having a half filled p subshell, it has a completely full subshell. All right, aluminum. Let's see here. So to find electron configuration for aluminum, right there, it's going to be 1s2, 2s2, 2p6, 3s2, and then 3p1. Okay. So again, so that's its ground state electron configuration, we're trying to form aluminum 2 plus. Okay, so what we're going to do is we're going to lose 2 electrons, all right? And so we're going to have to lose them, one from P and one from S. Okay, so they're basically taken out of the order in which they're added. They're taken away. Okay, so now that's the general case with elements that don't involve D or F subshells. When they involve D or F, it's complicated. It's a little bit different. Okay, you're going to have to remove them from S from your higher value energy levels. So the higher the energy, the quantum number, you have to remove those electrons first. All right, so let's look at one here for iron. So let me go back and we'll go through this process again to find the electron configuration for iron. I think actually we already did this one tonight as well. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, let's see, 1, 2, 3, 4, 5, 6, 3d6. All right, so that's its ground state electron configuration. Okay, here I'm trying to find the electron configuration for iron 2 plus, so it's going to have to lose 2 electrons. So we're not going to pull them from the D subshell, we're going to pull them from the S, okay? Because you have a higher quantum number 4 compared to 3, so we're going to remove these higher energy values here. So these 2 electrons on the 4s are going to be removed, okay? And this would be the electron configuration for iron 2 plus, which is everything except omitting the 4s2 there. It should be there. We took that out, so it's iron 2 plus. All right, so samarium is a very large atom. So samarium's right here, Sm. All right, so we need to go through all of this. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, okay, and then we go, so 6s2, 4f, 4f5, 4f6, and that would be the ground state for samarium. Here. All right, so here we have electron configuration, 6. Now notice, let me go back here because that might be confusing. Even though this guy is shaded yellow, it's really green, okay? So that's how I got 4s6 and not 4s5, okay? Because this guy should really be down here. These two should be down there. Okay. All right. And if you notice the periodic table I gave you, I believe that's the case if you look at it. I believe there's just a space here, and then these two guys start right here. So just note the difference there in that in the periodic table in your PowerPoint versus the periodic table that you have as a handout. That's important because you know the periodic table that you have as a handout is going to be the one you're going to have for the test. All right, so here you notice with samarium, we need to lose 3 electrons. So we're going to lose 2 out of the S subshell, okay? And then we're going to lose 1 from the F. Okay, so we pull out from the electrons out from the subshell with the higher N value, okay? And then once that's exhausted, then you have to actually pull out from an F subshell. All right, but for D or F, you're always going to pull out of that S first if you can. Okay, and then when that's gone, then you have to pull out of an F or a D in terms of electrons. Okay, So that's how you roll out electron configuration for ions. Okay, and again, if it's positively charged, you're going to remove electrons. If it's negatively charged, then you're going to gain electrons. A lot of times, when you're talking about representative elements, those electron configurations are going to be that of noble gases. Okay, sometimes when you're talking about a D or an element in a D or an F subshell, its electron configuration is not going to be that of a noble gas for most of the time. So there's a reason why we call them representative elements, because they're easy to sort of understand. And just to recap what a representative element is, it's group 1, 2, 13 through 18. So pretty much all the groups except the transition metals, basically, which they are more complicated to predict, And that's why their oxidation numbers are not always, like, for example, group 1s are always +1, because it's going to have the same electron configuration as a noble gas when it becomes an ion. But for transition metals, you notice that it's not the case. And so that's why they have, you have variable oxidation numbers for transition metals, because, their energy values are different. All right. So our next section here, we're talking about variations in element properties. We're going to talk about atomic size, ionization, energy, and electron affinity.